Okay, this chapter we're going to discuss a very unique type of energy called nuclear energy. Okay, the title is Fires from Nuclear Fission. The reason we call it fires because of showing these pictures. These energy could either be utilized nowadays to generate electricity, and also the fire is one of the main, most dangerous high impact weapon in the world nowadays. Okay, so in this chapter, we're going to study a few parts. Okay, the first part, very briefly, we're going to take a look how much energy is used in the world and the types of energy, and what are the trends for the percentage of these different types of energies. And then we're going to take a look how do nuclear power generates electricity, how do nuclear power is used in generating electricity, and what are the environmental impacts relative to fossil fuel power plants. And then the third part, I think I did change the order of these two, we're going to talk about a natural phenomenon called radioactivity, and what is radioactivity, and also what are the applications of using radioactivity and using radioactive elements in energy production as well. So basically there are three parts in this chapter, and tonight we're going to complete two parts. First is very briefly take a look at the energy used in the world, and also learn what is a nuclear power plant and how it is constructed, and how nuclear energy is used to power nuclear power plant to generate electricity, and what are the impact of using nuclear power. Okay, so let's take a look. First is the chart showing the source of electricity. So nowadays these are the ones we use to generate electricity, and of course the top ones, orange, purple, and blue, or is that purple, blue? Yeah, these are the three main source still, because they're fossil fuels. Okay, they're massively available. They're relatively less expensive to generate electricity. So you can see that they are still the major source for generating electricity, and also from 2015 you can see their trend is still increasing. But something to look at the trend, you will find out not all natural fossil fuel sources used in generating electricity is really increasing fast. Among these, you can see the natural gas and petroleum, they're still increasing, but you can see that the use of coal to generate electricity is actually what? Decreasing, right? The trend is flat out or even a little decreasing, and also demonstrate that we're trying to use cleaner fossil fuels to generate electricity than relatively dirty fuels such as coal. And then the bottom two are renewable sources and nuclear sources. And so among these five types, nuclear power to generate electricity still is a small fraction. Okay, even though it is a fraction, but it's still relatively small. A percentage of electricity is from nuclear power. And also you can see that the change of nuclear power is not that significant. It's very flat. That means we're still in an early stage of developing nuclear power plant. One of the main reasons, again, safety is one reason. Another reason is the cost of building a nuclear power plant is too much compared to a tritium. And of course the green line shows renewable. What is renewable? Wind power, solar power, and hydropower. These are renewable sources, are actually increasing very fast compared to all of the three types. Okay, so that's the trend for source of electricity. And this chart shows you the world energy production by source in 2019, this particular year, kind of give you an idea as we talked about before. You can see that the main sources are still these fossil fuels. Okay, some of these fossil fuels, gas, coal, and are these fossil fuels. And of course, other than that, these renewable sources such as hydro, solar, wind has a big percentage, but nuclear power is around 10%. Okay, that 10% remains very flat throughout the years. Okay, of course, this chapter we're going to talk about nuclear power, even though it is 10%, but it is one of the solutions to give us a lot of energy for electricity. So this is the picture, okay, taken from like the nuclear ORG, like International Nuclear Safety Center. Okay, this is the picture taken in 2005, but the total number doesn't change much. Okay, there may be one or two retired, maybe a couple built, but the number is around 440 power plants, or to be more specific, 440 power reactors across the world that generates 10% of the world electricity. Remember, the nuclear power is 110%. And you can see that most of the nuclear power reactors are located where? East America, Europe, and what? East Asia, mainly in Japan. Okay, China has a few, I think I remember 2 or 3, but mainly in Japan. Japan has a lot of nuclear power plants. Okay, and if you look, United States, okay, we know nuclear reactors are centralized in the east, southeast, and northeast, and midwest part. You can see this is the map showing as of mid-2019, nuclear power plant operates at 59 sites in 29 states. Okay, some states it doesn't have one. South Carolina, you guys can guess, or do you guys have any idea how many?
7.
We have 6 nuclear power plants. Okay, the closest to us, I don't know, closest to us, Columbia one is around here. I think this one. Okay, this one. It's in Summer. Is that one? Robinson. Oh, which one?
There's one in Rock Hill.
Yes, that's the one we're talking about, Rock Hill, called Catawba Nuclear Power Plant. And since you're talking about this, is the picture I took with one of the CHEM 105 classes. Okay, you guys, just 2 of you, but one year before COVID. Okay, after COVID, this program stopped. But before that, we actually took CHEM 105 students. Okay, after we studied chapter 7, we actually went into the nuclear power plant. We cannot go to the reactor, but we can see that. But we can actually get into the generator, the power plant inside the power plant. We can drive around the reactor. Okay, nobody can get into the reactor, but we can drive around the reactor. Okay, and you will be amazed if you get a chance someday to see a nuclear power plant. The security is way more secure than a prison. Okay, the guards are machine guns, holding machine guns at the gate, and of course metal detectors. You have to pass through the security, but the guards are not like TSA guard. They're really held machine guns. Okay, if you drive near, or if you want to try to get across the fence of reactors, there are a lot of fences for reactors, they will actually shoot you, most likely. They have drills and what this kind of thing happens, because again, safety impact, right? So again, if you got a chance, it's a very nice tour. It's a very amazing tour. Okay, so those are some background about nuclear power, and so let's get started to answer the question, what is nuclear power, and how do we use the nuclear power to generate electricity? So basically, we're going to take a look, what is the construction of nuclear power plant? So first, the energy from nuclear process, especially the one that is used to generate electricity, is a very simple reaction called nuclear fission. Okay, this word fission is kind of what? Kind of the cut split. Okay, the definition of nuclear fission is showing this kind of like moving picture. Is when a large nucleus, okay, large nucleus, like this, is hit by a small particle. Okay, later on we know the small particle is most likely a neutron. And then it will split into 2 relatively small ones. And this process will release a lot of energy. And the energy will be used to generate electricity. Now, there's some question. The reaction is simple, like demonstrated here, but there's something to clarify before we even move on for this chapter. First is, this chapter, technically speaking, is not chemistry. The reason is, you guys have studied 6 chapters chemistry. In chemistry, what is changing? What is going on between atoms? What part of the atoms is changing? Think about when we talk about covalent bond, what atoms do? Share electrons, right? When it comes up ionic bond, what atoms do? Losing and gaining electrons, right? Transfer electrons. So in chemistry, what is happening between atoms is only what? Electrons. To be more specific, what electrons? Valence electrons. Is that right? The atoms themselves don't change. We studied in chemistry for 6 chapters. Atoms what? Simply do what? Rearrange. In this chapter, it's totally different. There's no electron. What's happening for these reactions, like here, this one, they're what? They're nucleus. What is nucleus? Only the core. What is the nucleus? Proton plus what? Neutrons. There's no electrons involved. And when the large nucleus split into smaller ones, means what? The number of proton and neutrons are both what? Changed. So in nuclear process, the atoms themselves actually change for a different atom or different element, because we're not talking about atom, we're talking about the nucleus, no electrons. So technically speaking, like I said, this chapter we're actually not talking about chemical process, we're talking about physics process. Does it make sense? Okay, the nucleus is actually changing. Okay, here fission again, a large nucleus is split into 2 small ones. And in the process will release energy. Now, when it comes to fission reaction, we have to talk about a very important nucleus or element, uranium. Uranium, this element is found predominantly as 2 isotopes. Okay, what are isotopes, guys? We studied in early chapters. What are isotopes?
Different variations.
Same number of protons, different number of
Neutrons.
neutrons. Okay, neutrons. Very good. Okay, because they have different number of neutrons, they different number of what? Mass number, right? Uranium is found in 2 isotopes, uranium-235 and uranium-238. Of course, uranium-238 is the main isotope. Uranium-235 is only less than 1% in the mixture of uranium ore. And also, because this chapter we're going to talk about the protons, neutrons, and mass. Remember this notation, guys? In the symbol, left subscript is what? The proton number or atomic number, right? The top left superscript is what?
Mass number.
The mass number, which means the number of protons plus neutrons. Okay, we will use this a lot. This one and that one a lot. To represent the nucleus of these chapters. Now, the reason we want to talk about uranium when we talk about fission reaction is because today, as of today, uranium-235, which is less than 1% of that uranium ore we found, is the only naturally occurring isotope that can undergo the fission reaction. What is fission? The one we use to what? Generate electricity. A naturally occurring isotope, the only one that is uranium-235. That's why uranium is important. And of course, nowadays we no longer solely rely on uranium. We have other isotopes that is synthetic. Okay, that is naturally occurring. This is called naturally occurring isotope that can undergo fission is uranium-235. Good? Okay, keep in mind what is fission and what is uranium. Why we talk about uranium? Because uranium-235 is the material for what? For fission. Okay, now before we do that, let's do some quick practice about that notation. For isotope X, 5111119, what is the element? What element is X 5119?
Xenon.
No. X is not a symbol. X is just unknown. And ask you to tell. Which number do you look for?
It's 10.
50, right? What is 50?
10.
10, right? Okay, that's so the element is 10. What is the symbol for 10? SN. Okay, S. Very good. That's the element is SN because you tell by what? By the atomic number, 50. Very good. Number 2, how many protons, neutrons, or electrons in carbon 12? 6 protons, 6 neutrons, and what? 6 electrons. Very good. Here, how many protons, neutrons, and electrons are in chlorine 35? 17 proton, 18 neutron, and 17 electrons. Perfect, guys. Okay, again, the reason we do this, I want you to get used to the same sign, the notation, because we will use them a lot. All right, so now let's take a look at a fission reaction. This is just one example. Okay, just one example. There are many other fission reactions, but this is one of them showing you what is fission. Like I said, fission is what? When the large nucleus, uranium-235, is hit by a particle, the particle is usually a neutron. Okay, neutron. And then split into what? 2 smaller particles and release 3 more neutrons. Okay, this is a typical fission reaction. Now, in order to represent this fission reaction in an equation, because in chemistry we always want an equation, here is the equation. Okay, first take a look at these symbols. First, the particle is neutron. What is a neutron? Neutron is a particle with 0 charge and what? 1 mass. Is that right, guys? We know neutron has no charge, but the mass number is what?
1.
Is 1. So N01 is the symbol for what? For neutron. When neutron hits uranium-235, okay, technically speaking, when the uranium takes the neutron in, uranium-235 will become what? Uranium-236, which is not a stable isotope. So this guy will split into what? Into 2 smaller nucleus. In this case, okay, in this example, is barium-141 and krypton-92. And then the same time, 3 more neutrons are released. You hit by a neutron, you generate what? 3 more neutrons. 3 neutrons, not 3 more. 3 new neutrons. Now, this is the equation. How do we demonstrate a fission reaction? And also, if you take a close look at the equation, you will find out, just like chemical equations, something are balanced. In a fission reaction, because we have 2 sets of numbers, right? Atomic number and what? Mass number. And if you look at the fission reaction, you will find out on the left and right side of the arrow, the atomic numbers are balanced. The mass numbers are also balanced if you add them all together. Okay, I put it here. The superscript means what? The mass number, right? 1 plus 235 is what? 236. 141 plus 92 plus 3. Why 3? Because you got what? 3 neutrons. So 141 plus 92 plus 3 is 236. That means what? The mass number is what? Is balanced. The same atomic number, 0 plus 92, 92. 56 plus 36, 92. Neutron has no atomic number, so neutron atomic is 0. Okay, that's why I put it in red. Okay, not only we want to show an example of a fission reaction, but I also want to tell you, in all nuclear reactions we're going to study in this chapter, you have to make sure what? The atomic number, or we call the subscripts, and the mass number, or you can call it the superscripts, are what? Are balanced. Does it make sense? All right. With that, I hope you guys to practice these two. Okay. Why do we practice these two? Because sometimes they will give you some information, ask you to figure something out. Okay, ask you to figure something out. For example, the first example, ask you, hey, uranium-235 fissions to form Ba-138 and Kr-95 and neutrons. Ask you to write it down. Then how do we write it down? We know fission means what? U-235 is hit by a neutron. And then we give, the question tells us barium. Barium is what? 56, 138. Krypton is what? 36 and 95. And they said neutrons, and they didn't tell you how many neutrons. That's where you need to what? Play the balance game. Right? 1 plus 235 is what? 236. 138 plus 95 is 233. So that means what? You got 3 mass numbers short. That's how many neutrons you get? 3 neutrons. Okay, they didn't tell you. Most cases, fission reaction does give 3 neutrons, but not all the case, such as the second example. Okay, second example. It tells you 235 uranium-235 fissions to give you an element. It didn't even tell you what the element is. They just tell you what the atomic number is 52, mass number is 137, and another one, atomic number is 40, mass number is 97. In this case, you need to what? You need to use your periodic table to figure out, hey, what is the atomic number 52? Tellurium. What is the atomic number 40? Zirconium. You have to put the symbol as well. And then you have to do the math number again. 236 on the left, 137 plus 97 is what? 234. That means what? You have 2 mass numbers short. That means this game you only generate 2 neutrons. Okay, that's why I want you guys to practice. These questions are easy, but you have to get an idea of what? Of what is fission. Fission, you have to start with a neutron hit a fissionable isotope, mostly uranium-235. And then you have to, based on the periodic table, to figure out what? What are the daughter or the split particles? Make sense? All right, next. Okay, next. Remember fission. Okay, remember fission is 1 neutron split a uranium-235, then generate what? 3 new neutrons. This means what? This means what? These 3 new neutrons can potentially what? Hit another 3 uranium-235 to generate how many more neutrons? 9 neutrons, because each 1 neutron can hit a new uranium-235 to give 3 neutrons. If you have 3 neutrons here, if they hit another uranium-235, each one respectively, they can actually generate how many neutrons? 9 neutrons. Does that make sense? And those 9 neutrons can hit another 9 uranium-235. What's going on? That means this reaction can open what? Open up very fast. Because 1 gives 3, 3 gives 9, 9 gives what? Can hit more. So the reaction, once started, can open up in a very fast way. And we call this type of reaction a chain reaction. What is a chain reaction? Like you start at the first chain, the kind of like a fuse, you light the firework, right? The fuse can go up what? By itself. Does it make sense? Now, chain reaction is possible, but in reality, you don't see chain reaction a lot. The reason is, remember, uranium-235 only has what is the percent? Less than 1%. Means what? If you have a uranium sample, most of the uranium is what? 238. So that means once you have some neutrons generated, the neutrons normally cannot hit another uranium-235, but instead is actually absorbed by what? By a 238. Why? Because there are too many 238s around it, right? Uranium-235 is just too little. So that means in reality, chain reaction, you don't even see that. You still have to keep giving neutrons if you want to sustain the reaction. Because the neutrons formed from fission are mostly absorbed by what? By the non-fissionable uranium-238. Does that make sense? Now, another question. We know in reality you don't see chain reaction. But what if we do have a sample with all uranium-235? No 238. We have a way to do that. What happens? You got a what? Chain reaction, right? Remember this reaction, what? Release energy. And you release energy and you release more energy, release more. So all of a sudden, if you really have a chain reaction like this, energy can be released in a very, very quick and explosive way. Because we're talking about nuclear reaction. What do I mean explosive way? Atomic bomb. Okay, this is showing two pictures of the real atomic bomb. Sometimes it can even cause lightning. In order to sustain that chain reaction here, you at least need 15 kilograms of uranium-235. If you have that amount, you basically have an atomic bomb. And that mass is called the critical mass. If you have 15 grams, around 33 pounds of uranium-235, you got atomic bomb. Think about how much. 33 pounds, not a lot, right? Just a piece of your uranium, you get an atomic bomb. Have you guys studied history? When was atomic bombs used in real war?
1945.
1945, right? In World War what? Two. These are the two atomic bombs actually used, dropped in real war. That's the only chance. The first time and only time ever. Okay, the first atomic bomb dropped in Hiroshima is called Little Boy. Okay, and the second one is called Fat Man. They're named by what they look like. The one is a little smaller. But to clarify, the first atomic bomb is fueled by uranium-235. Okay, it is actually fueled by uranium-235. The second one is actually not. It's fueled by plutonium-239, which is synthetic fissionable element. We know uranium is the only naturally occurring one, but we can synthesize. Okay, we cannot only rely. So the second one is actually not by uranium-235, but by plutonium in Nagasaki. Okay, these are the two atomic bombs by fission reaction. Good. Next. So this chapter is very interesting. They're around us, but not really around us. Okay, you don't see them in real life, but they are actually around us. Like South Carolina, even not a big state, we have 6 power plant. Okay, 6 nuclear power plant. Now, next question is, why on earth a fission reaction, tiny amount of fission reaction, can generate so much energy, can cause atomic bomb, can make an atomic bomb? The reason is the mass. Okay, the reason is the mass. We know in a fission reaction, we do what? We do balance the atomic number and also what? The mass number, right? They're balanced. We still call it balanced. But in reality, if you keep all the decimals, these mass numbers are whole number. That means they're rounded. If you keep all the decimals like these, for example, the reactants, the mass number, okay, the reactants product, the mass number, 92 is actually 91.9. 141 is actually 140.9, and 3 neutrons are like this. So if you keep all the decimals and add them together, again, you will find out, the mass of the product is not exactly the same as mass of the reactants. Of course, if you run them, they're still 236, right? But if you don't run them, what's going on? The mass of the product is actually what? Smaller than the mass of the reactant. How much small? This much small, tiny amount of small. Okay, this difference is called mass defect. Okay, mass defect. What's mass defect? Mass defect means during a fission reaction, even though the mass is balanced, but the product mass is actually slightly less than the original mass. It means some mass is what? It's gone, right? You lost some mass. And your mass cannot just go in, cannot just disappear. It must go somewhere. And somewhere is what? Is energy. The mass loss defect is actually converted to energy using Einstein's famous equation. Delta E equals to delta M times C squared. Okay, C squared. Delta E means what? Energy change. Well, how much energy is released? Delta M means what? Mass change. How much mass is defect? Now, we know mass defect is what? Tiny, right? How could this tiny number becomes a huge amount of energy? It is actually because of the C squared. What is C squared? C is the speed of light. What is speed of light? You guys remember? We studied in chapter 2. 3 times 10 to the 8th. Okay, 8th. So C squared will be what? 9 times 10 to the 16th. Is that a big number? It's a huge number. That is why even a small mass defect multiplied by 9 times 10 to the 16th will give you a what? A huge amount of energy. Okay, huge amount of energy. How much? Let's do a simple math here. Okay, simple math. Let's say if you were to keep all 6 decimals and compare the mass of the products on both sides, you will find out the mass of the products is less by how much? 0.1%, like 1,000th, that much less. Like 1,000th of the mass is lost, is defect. So, let's say I have a 1 kilogram of uranium-235. Okay, 1 kilogram, kind of half like a critical mass. If I have 1 kilogram of uranium-235, 0.1% or 1,000th is lost. Is how much lost? 1 times 10 to the minus 3, negative 3 is lost. Right? This is how much I lost. Because I start with 1, I lose what? 0.1%. So this is how much is lost. And then I use the mass change times, again, what? C squared. Okay, what is C squared? It's 3 times 10 to the ES what? Squared. So mass loss times 9 times 10 to the 16th. This is the answer. 9 times 10 to the 13th kilograms meter square per second square. This unit happened to be the same unit as the unit of energy, joule. So this means what? If you have 1 kilograms of uranium-35, you only lose 0.1%, 1,000th. You generate how much energy? 9 times 10 to the 13th. That means how many zeros after 9? 13 zeros after 9, right? Is that 13 zeros after 9? This is how much energy. 9 times 10 to the 13th. We know a 6. 10 to the 6th is a million. 10 to the 9th is what? Billion. 10 to the 12th is trillion. So we have 90 trillion joules of energy. This is how much? Okay, equivalent to 22,000 tons of TNT. Okay, 22. People usually describe explosive power using equivalence of TNT. Okay, what is TNT? Just some fun reading for you. This is the structure of TNT. TNT stands for trinitropoltoluene, which is discovered by Alfred Nobel. Okay, you guys know this name, Alfred Nobel?
Yes.
Okay, Nobel Prize is named after him because he blew himself up basically by testing these explosives, and in 1883. Okay, and TNT is a very highly explosive. We actually use TNT if you want to dug a tunnel, especially if you want to dug a tunnel in a mountain. Okay, like a train tunnel, TNT is very popularly used because it's highly explosive. Okay, 1 liter of TNT you can see because burning of TNT can generate a lot of gas. When you have a lot of gas, that means what? Highly destructive and highly explosive. Okay, so that's why normally people use TNT to describe the explosive power. And again, 1 kilograms of uranium-235 will release the same amount of energy of 22,000 tons of TNT. All right, so next are 2 exercises. Okay, I won't go over them because these 2 questions will be in your quiz. Okay, I think they're bonus questions, so take a look at them and refer to the questions we talked about before to answer these 2 questions. I'll give you some hint. Okay, first question, they ask you, hey, we know 1 kilograms of uranium-35 release how much energy? 9 times 10 to what? The 13th joule. So they say, hey, go back to chapter 4, search coal, find the best coal, and see if you want to release the same amount of energy using coal instead of uranium, how much coal you need. So you kind of give an idea, oh, coal compared to nuclear energy, you need maybe a lot of coal to what? To get the same amount of energy. So this is the first question. Okay, the second question, they can do backwards, is they tell you a nuclear power plant. They tell you they have 3 reactors. Each reactor generates how much energy per second. And then they ask you, hey, can you tell me how much energy can generate per day? And then based on that amount of energy, how much mass loss you need from uranium-235. You need to do it backwards. Remember, what do I mean backwards? Is in here we know from 1/1000th of 1 kilogram we generate this what? This much energy. And then the second question is basically ask you to calculate energy first, then do it backwards and say, hey, oh, in order to generate this much energy by these 3 reactors, how much uranium do we need? How much mass loss of uranium do we need? Like it. Do it backwards, right? Again, these 2 questions will be in your quiz. Okay, think about it. Just play with the numbers and play with the energies. Okay, so after that, let's take a look. Power plants. Okay, because we know now the reaction, we know the energy, where the energy comes from. So let's take a look. Using that equation, using that fission reaction, how does a nuclear power plant actually work? Okay, before we study, let's take a look back something we have seen before in chapter 3, a coal burning power plant, right? This is the coal burning power plant. How do we use the energy from coal? It's basically what? We burn it and use the heat from the coal to do what? To boil water, right? To convert water into what? High temperature, high pressure steam. And then the steam turns the turbine and then what? Generate electricity. And because the steam is in a sealed, high pressurized system, so the hot steam has to be what? Cooled down by a condenser back to the boiler to be boiled what? Again. So that means in order to cool down the hot steam, you need a large body of water pump circulating cold water to do what? To cool down the hot steam. Does it make sense? So this is what we have seen before, is how a coal burning power plant works. Now, with that, take a look. A nuclear power plant. Okay, nuclear power plant. And recognize something in common and something, of course, not in common. What do you think is in common? The water, right? Water becomes what? Steam. Steam what? Turns the turbine what? Generate electricity. And then the hot steam has to be cooled down to what? To pumped back to where? To the boiler. Those are the same. Is that right? Okay, the same. But what's different is you're not heating the water with what? With coal, you're heating the water with what? With heat from nuclear reaction. Okay, you're actually not heating water with nuclear reaction directly. You're heating the reaction from the heat of the nuclear reaction. And of course, everything inside will be in a doomed structure called the reactor. So that's something different. We're going to take a close look. Okay, this is something different from coal burning. Another thing, what is the different?
Cooling tower.
A cooling tower, right? This thing doesn't have. We don't have that for a coal burning power. The cooling tower. Why do we need a cooling tower? Because the heat from nuclear reaction is too high. So the temperature of steam will be higher than coal burning power plant. So the hot steam, in order to be cooled down, of course you need a large body of water, but even with a large body of water, the heat still cannot be fully released. So you need what? You need a tower to release what? The heat. So you guys probably, when you see a picture of a nuclear power plant, the first thing you see is actually not the reactor, it's this thing, because they're huge. Okay, huge. If you take like a picture of a nuclear power plant or a drone picture of a power plant, you actually didn't notice the reactor because the reactor, they're small. The cooling towers are huge. For example, this picture. Let's take a look how small. This is a typical nuclear power plant. These two are actually reactors. Okay, these are called the Byron nuclear power plant in Illinois. Okay, but they're all very similar. These two are the reactors. Do you see that? And of course, maybe those are the generators. You can see how big the cooling towers. And of course, cooling towers are release what? Hot steam. Okay, they're not reactive. They're not radioactive because you can see that the radioactivity is in where? Located in here. Nothing to do with the cooling tower. Somebody say, oh, what? The nuclear reactors are releasing waste into the atmosphere. They're radioactive. There's nonsense. Okay, that waste is a waste, but what a waste? Heat waste. Okay, they may increase the local temperature, of course, but nothing to do with radioactive materials. Okay, and here's another picture, okay, of the Catawba River, Catawba nuclear power plant, and these are the two reactors. Okay, these are two of the reactors. Now, after we see the nuclear power plant, let's take a look. What's inside a reactor? What are the fuels look like? What a reactor is played, and what are the nuclear reactors structured? Okay, structured. Now, in order for a reaction to be in a controlled fashion, okay, you have to build first a very stable reactor, of course, concrete structures with layers of lead, okay, to avoid the escape of radioactive materials and radioactive rays. But inside the reactor, okay, we have nuclear reactions. Okay, we have nuclear reactions. And the reactions is powered by what? Uranium-235. Is that right? The fuel, the basis of nuclear power plant is uranium. Okay, some power plant does use plutonium, but most use uranium. So let's take a look. What does the fuel look like? Okay, they're not mysterious, guys. You will see, oh, the fuel is crazy. The fuels are tiny pellets in the form of uranium dioxide. Okay, or sometimes people call it uranium oxide. Okay, they're like a blackish, like a Tootsie Roll. Okay, I didn't know what Tootsie Roll is until we were there at the power plant, they say, oh, they're the same shape. I know what it looks like, but I didn't know, oh, they're actually very similar to the size of a Tootsie Roll. And of course, the fuel are stacked together to form rod, and the rods are making a assembly. And this is how, here, the real picture. This is how the fuels are shipped to power plant. They don't make the fuel. They just get the fuel regularly by shipping trucks from those fuel manufacturers. Nuclear power plant get the shipment every 6 years. Every 6 months, they told us. Okay, they make rods and also put in assembly. Okay, very beautiful assembly. Okay, very beautiful assembly. And after you have assembly, the fuel assembly will be placed inside the reactor vessel. Most times, especially power plants in the United States, the fuel assembly is submerged in water. Okay, in water. Just regular water. Not tap water, but ultra pure water. Okay. What does water do? Water serves as, first, a coolant, of course. Number 2 is water serves as a moderator, because water has the ability to slow down neutrons. Remember, what does neutron do? Start fission reaction, right? If you don't want a fission reaction to go too fast, you need to what? Slow down neutrons to hit uranium-235. So water serves kind of like a very nice media to what? To control the fission reaction at a very stable rate. Now, with water as a media, to control the fission reaction is not enough. In a power plant, the real design is to place something other than water. Besides water, they place some other materials to block neutron, to prevent one neutron from hitting too many uranium-235. And those rods are called control rods. What are control rods? Control rods are just some few elements that can absorb neutron. That's why we call them neutron sponge. What do neutron sponge do? Take some extra neutrons away. Why? Because we don't want neutron hit too many what? Too many uranium-235 to start the reaction. We want the reaction to be a very stable rate, not a chain reaction rate. So the control rod serves as some sponge to what? To take extra neutrons away. Okay, commonly such as cadmium and boron, they're capable of absorbing many neutrons without themselves decaying. So this is the scheme show how does control rods work. Besides water, the moderator. When you insert control rods, means what? Neutrons are what? Taken away. And then the nuclear reaction will be what? Will be slow or fully stopped. If you lift the control rods, what happens? Nobody takes the neutron away. Then the reaction will what? Will fully engage. Does that make sense? Okay, that's a very common design for a reactor. Control rods and fuel rods are alternating with each other. During natural disasters, for example, earthquake or tornado, if there's some warning, nuclear power plant will fully insert control rods to stop the reaction. Okay, you don't want some natural disaster that's happening, the reaction is going on. You want to fully stop. So you can see in this picture, control rods and fuel rods are actually what? Alternating with each other. With control rods fully inserted, okay, control is fully inserted, the reaction actually stops. Now, the energy from nuclear reaction is actually doing what? Is actually doing what? This is the reaction, right? They're heating what? heating the water in the reactor themselves. Is that right? We call this part of water, you can see that's sealed actually, the primary coolant. This primary coolant has a lot of heat in it. And then the primary coolant is actually the what? The coal boiling what? The steam generator, the water. So you actually has two separate systems, right? The real system for nuclear reaction is inside where? Inside the real reactor vessel. And then the coolant inside the reactor vessel is hot enough to do what? To heat the water in the steam generator to generate what? Electricity. You guys see that? So even the water here is cooled down by the condenser, by the whole lot of big water. They have nothing to do with radioactive materials because everything is in where? In here. So the real reactor, which is the real reactor? This is the real reactor. Okay, in a separate sealed system. And that system is the one used to heat the water for turbine. Okay, the reaction themselves is not heating the generating the power at all. The reaction itself is purely provide what? Provide heat. Does it make sense, guys? Okay, so that's basically all the basics of nuclear power plant. Okay, primary coolant is absorb the heat from the nuclear reaction, then it heats far above its normal boiling point and circulate in a closed loop from the reactor vessel and then back again. So it kind of like a primary coolant is cooled down by the steam generator, right? And the steam generator is hot enough to what? To turn the turbine. Now, of course, when we study nuclear reaction, nuclear power plant, one thing we cannot escape or avoid talking is what? Is the risk. What if this thing breaks down? Right? What is the reaction breaks? The reactor or the reactor building breaks down. Okay, that's disaster. So far, we have two main nuclear disaster in the history of power plant. The biggest one, you guys all heard, is what? Chernobyl. Okay, it's Chernobyl. And by the way, you guys, chapter 7 discussion topic due next Monday is actually watch Chernobyl, a show trailer of the show, and I strongly recommend you to watch the first episode. It's free. I think it's Hulu or HBO. HBO, I think. Either way, it's on the website. Okay, do watch the first episode. That gives you a lot of info already. It's very high impact. And then there's a documentary showing what's real. But that show is very good. That show is very good. You have a big heart to watch it. It's very, just make your heart just impact a lot. Okay, then let's go back to Chernobyl. Okay, in 1986, the reactor 4 of the Chernobyl nuclear power plant meltdown. Actually, not during routine running, they're doing testing. Okay, doing testing. And during that accident, during that incident, 9 tons of radioactive materials, 10 times, 100 times as much as an atomic bomb, because of how big the disaster is, were hurled into the sky, and the wind blowing days and dust to north and west. Soviet Union wanted to cover it until European countries, I forgot which country, Sweden, or reported extremely high radioactivity in their clouds, in their sky. And then Soviet Union just felt there's no way they can cover that anymore, because all the radioactive materials were hurled above the sky of Europe, Western Europe. Okay, these are some real pictures. Okay, this is the real picture of the reactor 4. You can see it's completely meltdown. There's no reactor anymore. Meltdown means the reactor is gone. Okay, and what makes it worse is the control rods in that power plant were made of graphite. Okay, graphite is good control material, but graphite can catch fire. So during the explosion, there's a lot of graphites on the floor. Remember, these are what? Control rods. They're inside the reactor. They're extremely high radioactive. But what is worse? You guys watch the show, you will see that. First responders, firefighters, when they first came to the scene, they didn't know it's reactor meltdown. They thought it's just a fire. Somebody can actually pick up one of the graphite block. Died immediately. I mean, the hands burned, whole arm burned down immediately. All the firefighters died second day because they didn't know. They were right at the scene with no protection because they didn't know it's meltdown. Okay, it's very, guys, the first episode I strongly recommend you. Okay, and these are some more consequences. You can read how many people were injured, how many were dead at scene, and how many people were evacuated from their homes. Okay, until today, that town, Chernobyl, is still a ghost town. Okay, it's open now, but it's still a ghost town. And how many future cancer from the accident range from how many, and also radioactive particles in the environment, in the food chains, sometimes we even didn't know until today. And to cover it up, not cover it, to solve the problem because the reactor meltdown. Okay, robots cannot even work well in there. Okay, the solution back then, I guess it's still the best solution, is they make a concrete structure, kind of like a coffin, to cover the whole thing up and let the radioactive just slowly decay until maybe 100 years, 200 years later can open up. But they put a concrete structure, they call it sarcophagus, like this. Okay, and I think 30 years later they make a second layer, kind of like a reconstruct layer. To what? To cover it, so radioactive material doesn't go up. Inside is still a mess. It just like somebody dig a hole on the floor. You don't repair the hole. All you need is put something to cover it up. Okay, then deal with later, hundreds of years of later. But now again, like I said, the radioactive level is lower enough around in the town. I think it was opened for tourism. Okay, this is a picture I found online because people are actually visiting Chernobyl's now. Okay, Chernobyl's now. And also, if you watch that video, you will see that a lot of firefighters, and they call liquidators, okay, they sacrifice their whole life of radioactive exposure to work on that accident. Because a lot of them even don't have protections. And 1 minute at the scene, you will receive the amount of radioactive amount that you could receive in your whole life. 1 minute. So a lot of fighters, you will see that, watch the show, they have to clean the bricks, the debris down to the reactor. So they're taking turns. One person work 1 minute, that's it. If we have more, you will die. So they're just use person to actually labor to do that. Robot doesn't work, they send robots, but robot didn't work because the radioactive is too strong. Okay, that's the first incident. The second one, okay, the second incident happened recently, I think. I remember what. Do you guys remember what year? 2000?
Yeah.
10 years ago? 25? It's very recently in Japan, Fukushima. Okay, caused by two, but they're not by the Soviet Union. That one is caused by human. The first accident they had an investigation, they're caused by human. Even so, Soviet Union wanted to cover it up. But this is caused by natural disasters, tsunami and earthquakes. Okay, it also caused the meltdown of 3 reactors. Okay, you guys can read more about the impact. Okay, nowadays they're keeping checking the impact of this.
It was 2011.
2011, yes. It's very recently. Okay, Fukushima incident, and you have a link. They keep updating link. Like, for example, most impact for the United States is what? Because the Pacific Ocean, a lot of sea lives are affected by radioactive materials. Sometimes you eat, like seafood may contain those radioactive materials. Okay, because basically Japan and United States are what? Separated by Pacific Ocean. Okay, so you can read more on the link, and again, they keep updating the link with the impact of that incident. Okay, next, few more slides, we'll be done today, is we'll go back to uranium. And remember we said uranium naturally abundance is only what? 0.72%. Is that right? It's very tiny. If you use natural uranium with tiny bit of uranium-235, you cannot even have a reaction. The reason is the neutrons hit 235, the new neutrons would never hit another 235, they were actually taken all by 238. So in order to have a chain reaction, no matter for weapon or for power plant, you have to increase the percentage of 235 in the mixture. And that increase, the percentage, is called enrichment, okay, or enriching. Natural abundance is 0.72%. In order to be utilized in a nuclear power plant, the fuel, you have to at least have 3 to 4% of uranium-235. That's small, tiny percent. In order to have a weaponized uranium-235, you need what? 90%. Okay, that's atomic bomb. That's a weaponized uranium-235. But either way, you have to increase the amount of 235, the percentage of 235 in the mixture. Now, this process seems easy, but it's very difficult. The reason is uranium-235 and uranium-238 were essentially the same, no matter chemically or physically. They're the same thing because they're isotopes. The only difference is what? Their mass number. How much different? 3 different. Still tiny difference in their mass number. So the trick of separating these two is based on that difference. Okay, mainly we're talking about 2 technologies. I don't know, this is something I learned, but I'm not, I guess, an expert later. You can read more about these 2 technologies. The first one is to convert uranium ore, after you get the ore, you convert it into a gas, UF6. It's a gas compound, containing uranium. Then you separate the chamber with a membrane and put pressure on it, and you will find out with the pressure, the lighter ones with more U-235 will be on one end, then the other end will be with more what? Uranium-238. So because of the pressure, the gas can diffuse. Lighter one can diffuse to one end, heavier one to another end. You can get what? You can get more enriched 235. That's called a gas diffusion. Okay, another technology, I think this one is used more, is after you convert it into gas, you spin it like your washer, like a centrifuge. When you spin it, what happens? The heavier ones will be where? The heavier ones will be where? Will be down, right? Lighter ones will be where? Up. Because think about it, you spin hard, right? So in this, you can collect uranium-235 after spinning. We call that gas centrifuge. Okay, gas centrifuge. Right? Spinning, your uranium-238 will be on the side, on the bottom, and uranium-235 will be at the center, so you can collect them. Okay, you can collect them. Now, after we get more uranium-235, we call this enriched uranium-235. But we also have a name for the part with more 238. Remember, you can take more 235 out, you end up with more what? 238. And we also have a name for that. We call those depleted uranium. What is deplete for? Deplete means you take the 235 away, right? The percentage of this uranium is actually more 238 now. We call those depleted uranium. Okay, depleted uranium is actually also used in wars, in making weapons. Okay, this is showing depleted uranium is used to actually tip bullet shells. Because the property of uranium, they can actually pierce tank. That's called an anti-tank shells. Okay, this is an anti-tank shell tipped with uranium-238. And finally, like I said, nowadays we're not only relying on uranium-235. Okay, more power plants are actually using a synthetic fissionable isotope, plutonium-239. It is synthesized from uranium-238, in fact. And plutonium-239 can also be used in a conventional reactor. A lot of power plants are using plutonium-239, including the one I just showed you, even the Fat Boy atomic bomb is fueled by plutonium-239. Okay, this is a picture showing a staff member is inspecting a fuel assembly before entering into reactors. Okay, they can touch it. They're not dangerous or anything. Remember, the amount of uranium-235, even if they're using uranium-235, the percentage is what? 3 to 4%. It's a very tiny percentage. Okay, but if you have a high percent, like for example, okay, if you have a high percent of plutonium-239, you do get atomic bomb. Like I said, the Fat Boy dropped on Nagasaki was fueled by plutonium. Okay, this is a picture of a weapon-grade plutonium. Okay, they make it to a ring size because they want to make it more stable, less concentrated material. Okay, this ring has a purity of 99.96 of plutonium, weighs 45.3 kilograms. Okay, this is enough plutonium for one atomic bomb core. Right, so that's all for today. We talk about fission reaction, fission materials, the structures of nuclear power plant, also some backgrounds of it. Hopefully you found it interesting, and please work on the web assignment for chapter 7 and also the discussion for Chernobyl. Right? I'll see you guys Thursday.